So we're here at the example table, and in this video we're going to be looking at some related rates examples. So you should be familiar with the idea of equations relating two different quantities. So say the area of a square is equal to L squared, the side length squared, things like that. Well, with related rates, we're going to be using these kind of relationships to determine a rate of change of one of these quantities given the rate of change of the other. So let's go right into an example. So we'll use this one. So we'll suppose that a square's side length is increasing at a rate of 3 inches per minute. So suppose that a square's side length is increasing at a rate of 3 inches per minute. So we want to know how fast the area is increasing when the side length is 10 inches. So how fast is the area increasing when the side length is 10 inches. So we'll start with the same equation. A equals L squared. A is the area, L is the side length. So now we're going to differentiate both sides. But we're going to differentiate both sides with respect to t, right? Because this is changing with respect to t. And we're looking for, the side length is changing with respect to t. And we're looking for the change in area with respect to t, right? Time. So on the left-hand side, we have dA dt. And on the right-hand side, we're going to need to use the chain rule, because L, the side length, is implicitly a function of t. So when we differentiate that side, we get 2 times L to the first power, right, by the power rule, and then that times the derivative of L with respect to t, which is dL dt. But dL dt is given to us. This thing is 3 inches per minute, right? That's what we're told. The square's side length is increasing. So this thing is equal to 3. And we're looking for dA dt when the side length is 10. So we also know what L is. So dA dt, where we're looking for it, is 2 times 10 times 3. So this is 60 square inches per minute. Let's look at another example. So this time, let's suppose that a cube's volume is decreasing at a rate of 5 cubic feet per second. So suppose that a cube's volume is decreasing at a rate of 5 cubic feet per second. We want to know how fast the side length is decreasing when the volume is 216 cubic feet. So how fast is the side length decreasing when the volume is 216 cubic feet. Well, where do we start? Let's start with the formula for volume. Volume equals side length cubed. Just like before, we can take the derivative of both sides. And just like before, we're taking the derivative with respect to t. So we get dv dt equals 3L squared. And then again, by the chain rule, we multiply by the derivative of L with respect to t. So times dl dt. And let's actually pause right here. This is the thing we're looking for, right? How fast is the side length decreasing? We want the rate of change of the side length. That's this. Right, so we had better be given these other two things, and we are. Well, almost. We're given dv dt. That's this 5. But note that it's decreasing, so we need to put in negative 5. Okay, so negative 5 equals 3L squared. Well, what's L? We're not given it directly, but we're told that the volume is 216 cubic feet. This implies that L is the cube root of 216, and that is 6. So negative 5 equals 3 times the 6 squared times dl dt. Now all that's left to do is to solve for dl dt. So we have negative 5 equals 3 times 36. 3 times 36 is 108. So we get negative 5 over 108. So that's dl dt, but how do we phrase that in words? It's always good to be able to translate this back into words. This negative means that the side length is decreasing. Of course, we knew that because the whole setup, volume is decreasing, side length must be decreasing. But that's how we interpret this. So, side length is decreasing at a rate of 5 over 108 feet per second. And there are some related rates examples.